Hello students, I am Vinay. I am discussing the load calculation numerical. Subject name is refrigeration and air conditioning, in which the air conditioning include the load calculation numerical. This is load calculation numerical in which a conference room is given. This is a conference room. I got this con given in which 80% sitting arrangement is given. The inside condition of the room, the inside condition room is given that 22 degree dry bulb temperature and 55% RH, and the outside condition, that outside condition is given that 38 degrees Celsius and 38 degrees Celsius dry bulb temperature, which is measured by ordinary thermometer, and 28 degrees Celsius wet bulb temperature. This is condition number 1. This is condition number 1. This is condition number 2. As I draw further, that is point number 1, outside condition. That is point number 2, the inside condition. And after this, there is a sensible heat and latent heat per person. This is the sensible heat per person. That means this is the latent heat per person. That means total 80 persons are sitting in the room. We have to multiply the sensible heat with the 80 and latent heat with the 80. Both factors we have multiplied with the 80 to calculate the total amount of 80% sitting in the room. After this, the light load is given, light and fan load. That's mean light and fan load is considered as a sensible heat case, because in this there is no increase in humidity or decrease in humidity. At constant humidity there is increase in temperature, only increase in temperature. There is no change in humidity. That's mean 12,000 watt, that is 12 kilowatt. And the sensible heat, it is given that sensible heat gain through glass, wall and ceiling, it is also 12 kilowatt, 12,000 watt. The infiltration air, that's mean the outside air at point number 1, which is directly enter into the inside condition. That is our inside condition, that is our outside condition. The outside condition is directly enter. That's mean that outside condition, is directly enter into the inside condition. That outside condition is point number 1, which is directly enter to inside condition. This is point number 2, which is all further explained in psychometric chart. You have to check out video further. That is the infiltration. The infiltration is that air which is forcefully enter into the room without providing any ventilation, or we are providing any inlet to the air to the room. That is directly enter from outside to the inside. This is outside condition is given, and this is the inside condition is given. That's mean after this, the fresh air supply, that's mean 80 meter cube per minute. This is the volume flow rate is given 80 meter cube per minute. That's mean if bypass factor is given, that is 0.1. If the 2/3 of the recirculated air and 1/3 of the fresh air, that's mean 1/3 of the fresh air, that is the fresh air, 1/3 of the fresh air, 1/3 is 33.3%, and 2/3 of the air is 66.6%. 66.6% is recirculated air, 33.3% is fresh air, which is entering to the room and mixed before entering the cooling coil. That's mean explain this one by drawing a graph. I also further explain these in a brief in psychometric chart. This is our point number 2, inside condition of the room. This is our outside condition. This is point number 1, which is given as, this is point number 1, this is point number 2, which is given. That's I rub all these things to explain you in a easy way. These are, if I will discuss, wait a minute for a second. So right now, this is the condition number 2, this is the condition number 1, this is inside condition, this is outside condition, this is inside condition, this is our room, and this is outside condition. And 2/3 of this room air, 2/3 of the room air is recirculated and mixed with 1/3 of fresh air. This is 1/3, this is 2/3 is mixed before entering the cooling coil. That's mean there is a mixing chamber over here. that two third of recirculated air, one-third of the fresh air is mixed with two-third of the recirculated air, after which there is a cooling coil. These are the cooling coils, and after this passing through the cooling coil, it is entered into the room. That's mean point number 1 is our outside condition, point number 2 is our inside condition, point number 3 is after mixing, this is point number 4 after passing through cooling coil, point number 6 is the coil temperature. That's mean 66.6% is recirculated, 33.3 is a fresh air. That mixing takes place, after which we go to point number 3, and after this there is a ADP, Apparatus Dew Point Temperature. After this there is a point number 4 which enter to the room. This is further explained in my video, so please watch that load calculation solution. I draw a psychometric chart for this numerical. Please look at. So I am going to the psychometric chart right now. Thank you. Please go through the whole numerical. It is the most important numerical with respect to load calculation. Thank you. Thank you.
Hello students, I am Vinay, Assistant Professor, Mechanical Engineering Department. Today I will discuss you Psychometric Numerical Part 2. In this, we are discussing the load calculation. First of all, I want to brief about the numerical, which is shown above in the video, that 80%, the total persons are sitting in a room are total 80 persons. Total 80 persons in a room. There is inside design condition is given. That's mean our auditorium is given, whose inside design condition is given. That inside design condition is 22 degrees Celsius, 22 degrees Celsius dry bulb temperature, and 55% RH. This is 55% RH. This is inside condition is given. After this there is outside design condition is also given. That is the outside design condition. This one is outside design condition. Outside design condition is given 38 degrees Celsius, 38 degrees Celsius dry bulb temperature, and 28 degrees Celsius wet bulb temperature. This is outside condition is given. And the sensible heat and latent heat per person के रिस्पेक्ट में, दैट्स मीन सेंसिबल हीट एंड लेटेंट हीट पर पर्सन, दैट्स मीन 75 watt is our sensible heat and 45 watt is our latent heat per person. Plus with respect to fan, this is the one condition for per person. After this, light and fan loads. If the light is in a room, that's mean the only sensible heat is increased. There is no change in phase, there is no contact with the water vapors, there is no emission of water vapors in the system. That's mean if there is a light or a fan, that is considered as a sensible heat case. That is considered as a sensible heat case. If we write down over here that sensible heat due to light, which is 12,000 watt, that's mean 12 kilowatt. Similarly, then sensible heat gain through glass wall and ceiling, through glass, the similar 12,000, that's mean 12 kilowatt. The air filtration rate is given as 18 meter cube per minute, and fresh air supply is 80 meter cube per minute. That's mean infiltration is given, fresh air supply is given, bypass factor is given in this numerical is 0.1. Two-third of room air is recirculated. That's mean the two-third of the room air, that is the room condition, the two-third of room air is recirculated, and 1/3 of fresh air. That means this is the fresh air which is outside condition. Fresh air, 2/3 of the room air and 1/3 of the fresh air are mixed before entering the cooling coil. That means they are mixed at this point. The mixing will take place. After this, there is a chamber at which the cooling will take place. After this, the air is entering to the room. This is the initial condition is given. We have to mark out the points. That is, outside condition is given as point number 1. Inside condition is given as point number 2. Point number 3, this is after mixing. This is point number 3. After mixing, the point number 3. After this, there is a point number 4. This is after cooling coil, the point number 4. Point number 6 is our apparatus dew point temperature, cooling coil temperature. This is mixing chamber. This is where the mixing takes place. This is the numerical is given. 80% sitting is there. There is sensible heat, latent heat per person, and sensible heat due to light, sensible heat due to glass ceiling. Inside condition is given 22 degrees Celsius and 55% RH, and all these parameters are given this numerical. We have to check out this numerical. So mark out the outside condition. First of all, we have to mark out 38 degrees Celsius and 28 degrees Celsius. That's mean 40. This is the 40 point. After this, there is 38 degrees Celsius. This is 38 degrees Celsius. We have to draw this one vertically. We are moving vertically at 38 degrees Celsius, up to which 28 degrees Celsius wet bulb temperature. You know that the wet bulb temperatures line are moving like this one: 30, 29, and this one is 28. That's mean this is 28. This is the cross section point where our point number 1 will exist. This is condition number 1. Outside condition is given. After this, it is clear. After this, the inside condition is given at 22 degrees Celsius dry bulb temperature and 55% RH. That's mean 20, 21, 22 degrees Celsius. This is 38 degrees Celsius and this is 28 degrees Celsius. This is WBT. This is DBT, dry bulb temperature. These conditions are given. After this, 22 degrees Celsius is our 22 degrees Celsius dry bulb temperature and 50% RH. That's mean 55% RH. This is our condition, and relative humidity lines are moving like this one. This is 60, this is 50. That's mean in between this there is a point that is at 55% RH. The condition is given. This is condition number 2. This is condition number 2. This is our condition number 2. This is condition number 1. The condition number 2 and condition number 1 is given in the numerical. After this, we have to find out the point number 3. That's mean there is infiltration of air is also exists. Due to infiltration point number 1 is directly entering into the point number 2. That's mean due to infiltration, the outside air is directly mixed with the point number 2 inside condition. That is known as infiltration. That's mean we have to draw a line. We have to draw a straight line. We have to join these two lines with a scale by the use of scale. This is we have to draw point number 1 and point number 2 because outside condition is directly mixed with the point number 2 due to infiltration of air. This is due to infiltration of air. After this, due to this infiltration, there is some amount of heat energy, the latent heat and sensible heat both adding to the system. That's mean we have to draw a line. This is a straight line, latent heat, and this one is a horizontal line. We have to draw a horizontal line which is sensible heat. Both cross at point A. We have to find out the enthalpy at point number 1, we have to find out the enthalpy at point number 2, and we have to find out the enthalpy at point number 1. That's mean enthalpy at point number 1 is that we have to move this forward line. This is our 90. This is H1. At point number 2, the enthalpy is 45, H2. And at HA, the enthalpy is approx, this is at HA 61, at point number this one 61.3 is equal to enthalpy at H point A. This is the enthalpy at point A. After this, we have to find out the specific volume. These are the specific volume lines. If we zoom out in this one, there is a specific volume line. These are the specific volume lines. If you are visible, these lines, these are specific volume lines. At this point, the specific volume is 0.85. At this point, it is 0.90. At this point, it is 95. That means there is 5 divisions in between that. We have to draw a straight line. We have to draw a straight line and divide this line into a 5 section. 1, this is 2, this is 3, this is 4. We have to draw these lines through a scale. That means this is 0.90, 0.90, this is 0.91, 0.92, 0.93, 0.94, this is 0.95. We have to draw these lines. That means at point number 1, we have to find out the specific volume. At point number 1, specific volume is V1. At specific volume is at this point is 0.9095. We have to just we have to draw with the scale. We have to measure the specific volume at point this. At this point it is 0.90. That means it is in between 0.90 and 0.91. This is the 0.91, 0.92, 0.93, 0.94, 0.95. That means it is approx value. We have to measure through a scale. It is 0.909, 0.901. It is approx to that. After this, we have to find out. After this, we have to find out the mass of infiltration air. Mass of infiltrated air. We have to calculate the mass of infiltrated air. That's mean that mass of infiltrated air, which is equal to mass of infiltrated air, which is equal to M1, which is equal to V1, the volume of infiltration, which is given at 18, and the specific volume at V1. That means the V1 is our 18 meter cube per minute. This is given in numerical, and we have to calculate the outside condition. At outside condition, the specific volume is given at 0.905. So that through this we will find out 9095. Through this we will calculate it is 19.79 kg per minute. This is our infiltration mass due to infiltration. After this, we have to calculate sensible heat due to infiltration. Sensible heat due to infiltration. That means M1 into HA minus H2. I will explain how can this we will find out. This is latent heat due to infiltration air. This is M1 H1 minus HA. We already calculated the value of H1 and HA through this diagram. This at point 1, the enthalpy at point 1, this is the enthalpy. This is the horizontal line shows the sensible heat line, and the vertical line shows the latent heat line due to infiltration. That means at 1 is directly entering to the point number 2. That is, point number 1 is directly mixing with the point number 2, due to which there is outside air having some sensible heat, outside air having some latent heat. Whenever there is no change in temperature but change in humidity, that means there is change in humidity, decrease in humidity, there is decrease in humidity, that means the latent heat reason. This is latent heat line due to infiltration. And whenever there is no change in humidity but increase in temperature from 22 degrees Celsius to 38 degrees Celsius, that means there is a sensible heating due to infiltrated air, infiltration, due to infiltration. This is the numerical. We have to find out the enthalpy as all the points. That means I will show you through zoom at these. That means at point number 1 we have to find out 90. Point number A, we have to find out enthalpy 61.3. At point number 2, this is point number 2, we have to find out the enthalpy at this one. That's mean this shows the latent heat, which is equal to H1 minus HA. This shows the sensible heat, which is HA minus H2. We will multiply this with the mass. That's mean HA minus H2. I want to zoom out this one. HA minus H2. If we are moving forward, this one. HA minus H2 sensible heat. This is I think this is given wrong. This point is HA, this is H2. That's mean this is sensible heat region. With the multiplication of mass, we will find out the sensible heat infiltration M1 HA minus H2. This is latent heat region. Latent heat H1 minus HA into mass. That's mean the latent heat is a vertical line, the sensible heat is a horizontal line. We will calculate the sensible heat and latent heat in both the parameters, in both the cases. After this, we have to find out we calculate the latent heat and sensible heat for both the cases due to infiltration. These are the infiltration parameters. Then per person, sensible heat due to per person. Sensible heat is given in the numerical is 75. We have 75 watt into 80 persons. That's mean this is 6000 watt. That mean 6 kilowatt. This is 6 kilowatt. Through this, we have to find out the sensible heating and latent heating. I will calculate this one also. The latent heat per person, which is equal to 45 into 80, which is equal to 3600. That's mean 3.6 kilowatt. That is our answer per person. Due to infiltration, we will get, due to sensible sensible heat, it is M1 is 19.79 into what is the value of HA? HA is 61.3 and minus 45. We will get the answer through this one. 5.38 kilowatt. I directly convert this into a solution. 5.38 kilowatt. Through this, 19.79 is the M1. HA value is 90 minus 61.63. These values are calculated from psychrometric chart. This is 9.36 kilowatt. This is the HA. We have calculated the value of HA at 61.3. H2, which is equal to 45 kilowatt per kg, and H1 is equal to 90 kilojoule per kg. That's mean we have to find out all the values for with respect to infiltration, sensible heat and latent heat due to infiltration, sensible heat per person, latent heat per person. After this, with respect to room, there is sensible heat gain through light. It is 12 kilowatt, and again sensible heat due to glass wall, ceiling, we got 12 kilowatt. That's mean we have all the parameters with respect to sensible heat and with respect to latent heat. If we calculate room sensible heat, we have to add all the sensible heat parameters. This is sensible heat parameter number 1, this is sensible heat parameter number 2, this is 3, and this one is 4. That's mean the solution of first is 5.38 plus second is 6 plus 12 plus 12. We have to add 3 and 4. That's mean total sensible heat of the room is 35.38 kilowatt. This is our room sensible heat. Then again we have to calculate room latent heat. That's mean room latent heat. What is the value of room latent heat? Parameter number A, parameter number B. We have to add both points. 9.36 through this solution, and this is latent heat per person is 3.6 plus 3.6, we get 12.96 kilovolt. This is, we got room sensible heat and room latent heat. After these parameters, we have to calculate the value of room sensible heat factor. This is the most important, room sensible heat factor. What is the value of room sensible heat factor? What is the formula? This is room sensible heat upon room sensible heat plus room latent heat. That's mean room sensible heat is calculated, room latent heat is calculated. We have to add this one. This is room total heat. So through this, I got the result. I finally write down the result 0.732. This is the most important which we got. So this is basic numerical. This is the load calculation basic. We have to calculate the all load, or we have to calculate all sensible heat factors. We add down the all sensible heat factor parameters, which we increase the temperature of the system. All latent heat parameters which increase the humidity level of the room. That's mean latent heat whenever there is no change in temperature but only phase change occur. Sensible heat, all the parameters with respect to room which increase the temperature of the room. There is no increase in humidity at this point. So by doing all these things, we got the sensible heat factor, room sensible heat factor, which is 0.732. That's mean this is sensible heat factor line. So through room sensible heat factor, we got the room sensible heat factor. This is sensible heat factor line. These are 1, 0.95, 0.90, 0.85. Our sensible heat factor value is 0.732. We already calculate on the previous page. This is our value which we got. This is the value 0.732. This is room sensible heat factor. That's mean we have to draw a room sensible heat factor line. This is 0.732. That's mean this is 0.70, 0.71, 0.72, 0.732. It is approximate about this point. This is 0.732. We got the value of 7.32. But we not directly join the point number 2 with this room sensible heat factor. This is room sensible heat factor point. So we have to find out, this is the constant value. We have to mark alignment circle. This is the alignment circle whose value is fixed at 26 degrees Celsius dry bulb temperature, 26 degrees Celsius dry bulb temperature, and 50% relative humidity. It is a fixed value. This is a fixed value for alignment circle. That's mean 25, 26. This is the 26 degrees Celsius for alignment circle. It is a dry bulb temperature. We measure the direct dry bulb temperature on horizontal line. This is a dry bulb temperature, and we have to mark this up to 50%. This is 40 and this one is 50. That's mean this value is alignment circle. We have to mark the alignment circle. We have to join this alignment circle with a room sensible heat factor. That's mean the scale is little bit smaller, but we have to draw a join room sensible heat factor with, this is the joining, this is alignment circle. We join the alignment circle with room sensible heat factor, which we calculated in the previous page. That's mean this we go align with the alignment circle. This is the line with alignment circle and room sensible heat factor. This is the most important line with respect to load calculation. We have to draw just a parallel line. We have to draw just a parallel line with this alignment circle which passes the room condition. That's mean our auditorium is to be maintained, or a conference room is to be maintained at point number 2. That's mean we draw a parallel line with respect to this, with respect to alignment and room sensible factor, which passes through the point number 2. Which passes through the point number 2. That's mean this is the condition. This is the condition on which our point number 4 will exist. This is the condition. This is parallel, directly parallel. The blue line, green line is directly parallel. The green line is directly parallel to alignment circle. I will zoom this one to show you clearly. That's mean that line, that green line is directly parallel to the blue line. This is parallel to the blue line, which passes through the point number 2. This is the point number 2. This is the room condition. We got this line. The point number 4, this is the most important, which is entering to the auditorium. Point number 4, which is entering to the auditorium or a conference room. The point number 4 will exist on this green line. This is our room condition. Whatever is increase in sensible heat, whatever increase in latent heat, all the parameters meet on this line. That's mean we got the room sensible heat factor line. This is our room sensible heat factor line. This is our room. This is based on our room. This is the final line which we got through all this calculation. This is the result. I will zoom out this one to explain further. So if I will explain you the numerical in the starting, this is our chart. This is our chart, and this is the initial inlet condition. That's mean 1/3. I have to check the numerical. This is 2/3. 2/3 of the air is recirculated, and 1/3 of fresh air is mixed over air. That's mean point number 2 is mixed with point number 1. This is 33%, 33.3% of point number 1, and 66.6% of point number 2 are mixing. That's mean this is point number 2. This is point number 2. We're taking out the 66% and add this 66.6% in point number 1. This is 33.3%. That's mean we have to measure this length. This is approximate around 10 point something. This is around 10.5. That's mean if we mix this 60%, that's mean if we are mixing point number 2, if we are mixing point number 2, that's means 66%, 66.6% in point number 1. That's mean there is decrease in temperature of point number 1 up to 66.6%. I explain you. The point number 1 is 33.3%. We take out this 33.3% and mix with 66. This is equal to 66.6%. And point number 1, it is 33.3%. We mix this is 33.3% outside condition, whose temperature is 38 degrees Celsius, very high. This 33% is mixed with 66%. That's mean 33% at 38 degrees Celsius, which mixed with the point number 2, which is at 22 degrees Celsius. There is increase in temperature. There is increase in temperature up to 33%. That means this line shows the 33%. If we take out the point number 2, 66.6%, and mix with the outside condition, it will decrease. How much amount it will decrease? 60. So after mixing 2, this is 66.6%. This is 2/3, 66.6%. We're taking out the 66.6% and mix with the outside condition. Then there is inside condition is 22 degrees Celsius. Outside condition is 38 degrees Celsius. That's mean if we are mixing 66%, so 66.6% at 22 degrees Celsius, which mix with the 33% at 38 degrees Celsius at dry bulb temperature. That's mean 38.3 degrees Celsius temperature is decreased down about 66.6%. We got the 3 point. If we mix this 38 degrees Celsius at 33% with 66.6% at 22 degrees Celsius, 38 is mixed with 22. That means there is increase in temperature up to which level? 33.3%. This is 33.3%. That means we got the point number 3. This is our point number 3. We directly check out at the dry bulb temperature at point number 3. It is 27 degrees Celsius. That's mean due to mixing point 1 and 2, we got the point number 3. Due to mixing of point number 1 and 2, we got the point number 3. This is due to mixing. There is decrease in temperature of 38 degrees Celsius. There is increase in temperature of 22 degrees Celsius. 38 degrees Celsius, which 38 degrees Celsius is decreasing. 22 degrees Celsius is increasing. We got the point number 3 due to this mixing. This is the point number 3. I have to explain that is the inlet condition to the cooling coil. These are the cooling coil. Inlet condition to the cooling coil is 33 degrees Celsius. Outside from the cooling coil condition is 4, and the cooling coil temperature is given as 6. That's mean I have to explain the bypass factor for the cooling coil. This is the condition for the bypass factor for the cooling coil. I have to explain first of all the bypass factor for heating coil, bypass factor for the cooling coil. We directly check out this one, that is 32 upon 31, that means TdB3 minus TdB2, TdB3 minus TdB1. Due to summer there is decrease in temperature, decrease in size of waste. This is the example for learning. That's mean in this case it is 2 3, that's mean 2 is moving forward and 1 is moving forward, divided by 1 3. We have to just to easily learn these things, I have to write this one. If you don't want to this one, you directly write down this one equation. That is the initial condition, inlet condition is 1, outlet condition is 2. This is the heating coils. These are the heating coils at temperature TdB3. These are TdB3 minus TdB2, TdB3 minus TdB1. This is bypass factor for heating coil. If we check out the bypass factor for cooling coil, this is the inlet condition at point number 1, outlet condition is point number 2. This is the coil condition for cooling coil. This is our cooling coil. This is TdB3. We directly write down TdB2 minus TdB3, TdB1 minus TdB3. But in our case, the inlet condition to the cooling coil is point number 3. Outlet condition from the cooling coil is point number 4, and the coil condition is at point number 6. We directly show you in the chart. This is the inlet condition at point number 3. Inlet condition is point number 3 to the cooling coil. Exit condition is 4. Inlet condition is point number 3. Exit condition is point number 4. And cooling coil temperature is as given as 6. So we have to replace 1 with the 3, 3 with the 6, 2 with the 4. That's mean there is TdB1. That's mean TdB3 is written as over here in place of TdB3, because inlet condition is replaced by point number 3. Outlet condition is point number 2 is replaced by 4. In this case, point number 2 is TdB2. In this case, this is TdB4. We have to replace. After this, the cooling coil is TdB3. We have to replace with TdB6. That's mean we got the formula for bypass factor for the cooling coil. The bypass factor in the numerical is given as 0.1, and TdB3 I already calculate from a psychrometric chart. This is point number 3. We got by the mixing, and we got the 27 degrees Celsius at bypass due to mixing of the system. That's mean TdB3 is given 27 degrees Celsius. We have to apply trial and error method for this equation. Trial and error method. That's mean we have two unknown parameters. We put the value of these two to got the result 0.1. This is bypass factor for cooling coil. We got the result 0.1. That's why I use the value of 9 and 7. We continuously change it 9.2, 7.2. After by doing all these experiment, we got the result 0.1 at these condition. This is TdB4 9.6 degrees Celsius and TdB6 is 7.6 degrees Celsius. Through this I got this result by trial and error method. So I'm now going to the our psychrometric chart. I will explain. This is TdB4. TdB4 is 9. This is TdB4. TdB4 is 9.6 and the coil temperature is 7.6. This is our temperature is 9.6. That's mean this is approximate 9.6 is approximate over here. This is the straight line, and we approximately this is I think this is lower little bit downward, moving downward. There is a small mistake in this one. We go over here. This is our point number 4. This is point number 4 and it is moving over downward. Clear? This is our point number 4. We directly join point number 3. We directly join with point number 3. 4 with the 3. This is point number 4. And what is the value of this? 7.6. 5, 6, 7.6. This is 7.6 and this one is 7.6. So in a straight line, these lines are moving. We got a little bit downward. We have got the point or a little bit downward. We have to join the point number 4 with the point number 3. We have to join the point number 4 with the 3. Through this we will go this point. This is our point number 6. This is our point number 6 at 7.6 degrees Celsius. The point number 4 is at 9.4 degrees Celsius. It is approx result. This is point number 4. This is point number 4 is our inlet condition. Inlet condition to the auditorium. This is 9.6 degrees Celsius and the coil temperature is 7.6 degrees Celsius. That is ADP, Apparatus Dew Point Temperature, where the condensation will start. That's mean we got the point number 4 which cuts over the green line. This is green line, this is our green line, this is room condition. Whatever is the temperature on 4, it passes through this green line, room sensible heat factor line. This is the room sensible heat factor line. So we have to mark the point number 4 over this line. Clear? Then there is 3 and 4, there is 3 and 4 on the same line, because 3 passing through the cooling coil and we got the 4. This is the 6 and 3. If we joining the 3 and 6 temperature, we got the point number 4. Clear? If we passing the point number 3 air with the cooling coil over the cooling coil, we got the point number 4. 27 degrees Celsius, which loses the temperature at 7.6 degrees Celsius of coil, we got the result at 9.6, which is inlet to the cooling, which is inlet to the system. So this is the overall chart. We got the final result which is entering to the room. This is the air which is entering to the room. This is entering to the auditorium. This is our room condition. This is our room condition or a conference room. We have to calculate all the parameters. We find out the room sensible heat factor line. We find out the point number 3. After the mixing, there is a point number 3. After the cooling coil passing through, we got the point number 4. We got the point number 6 ADP. Then after this, in this numerical, one more thing is asked, that is grand total heat. I will explain the grand total heat load. Grand total heat load, which is asked in the numerical. I will show you that in this case we have to find out outside air total heat, which is equal to, the formula is given, 0.02 VF volume of fresh air H1 minus H2. That outside air is directly enter into the room, which include, that's outside air one condition, which is directly enter directly enter into the room. That's mean there is sensible heat and there is, this is latent heat due to infiltration, fresh air. This is outside air latent heat due to infiltration, and this is latent, I'm confusing. This is latent heat, this is sensible heat. We got the enthalpy at point number 1, we got the enthalpy at point number 2, this is H1, this is H2. We got this result. This is the volume of fresh air given in the numerical. We got the result at outside air total heat is 72 kilowatt due to outside air. The total heat entering to the room is 72 kilowatt. That's mean grand total heat, which is equal to room sensible heat plus room latent heat plus outside air total heat, which is equal to room sensible heat we calculate in the previous 35.38. In the previous page we got 35.38 room sensible heat. Room latent heat is 12.96 plus 12.96 plus 72. That's mean we got result 120.34 kilowatt total total heat. It is our grand total heat. After this, one more thing is asked in this. There is effective room sensible heat factor. We directly join the point number 6. We directly join the point number 6 with the 2. We directly join the point number 6. We have to use the different color pen to explain you. We directly join the point number 6 with the 2. This is our effective room sensible heat factor line. So through this, if we move further this line, the effective room sensible heat factor line, this is moving on further direction. this is moving on further direction. We got this is effective room sensible heat factor, which is equal to 0.69. This is 0.69. So we got the effective room sensible heat factor. This is directly ADP is mixed with the point number 2. ADP apparatus dew point number 6 is directly mixing with point number 2. This is point number 2 and 6 are directly made. This is effective room sensible heat factor line, which is moving further to find out effective room sensible heat factor 0.69. So this is the numerical of load calculation. Thank you for watching this video. This is the most important numerical, which include the many aspects. It includes the sensible heat produced by the 80%, latent heat produced by the 80%, sensible heat produced by the light, Now I am briefing this numerical. In this, there is a auditorium is given, a common room is given at 55% RH, 80% are sitting in this room, 80% which have sensible heat at 75, latent heat as 45. Sensible heat due to lights in the room 12 kilowatt. Sensible heat due to glasses 12 kilowatt. Infiltration parameter is also given. We have to calculate the mass due to infiltration is 19.79. We will find out the specific volume at point number 1. These are the lines for the specific volumes. After this, we have to find out the sensible heat due to infiltrated air, latent heat due to infiltrated air. So I will summarize this psychrometry chart based on a numerical. This is the point number 1, outside condition. This is point number 2, the inside condition. 38 degrees Celsius, 28 degrees Celsius wet bulb temperature, 38 degrees Celsius dry bulb temperature, 28 degrees Celsius wet bulb temperature. We got the point number 1. At inside condition 22 degrees Celsius dry bulb temperature and 55% RH. This is 55% RH, relative humidity. These all are relative humidity. That's we got the point number 2. Then there is a mixing. That 66% and 33% of outside air is mixed with the 66.6% of room inside air, which is recirculated. That's mean the point number 2 is mixed with the 66% decrease in temperature. If the point number 1 is mixed with the point number 2, there is increase in 33%. We got the point number 3. At point number 3, there is a temperature 27 degrees Celsius. We got the point number 3, the 27 degrees Celsius. After this, there is a cooling coil in between point 3 and 4. The cooling coil temperature is 6. That's mean we have to calculate 3, 4, 6. Before this, there is 80% sitting in the room. That's means sensible heat is given for per person, latent heat is given for per person. We will calculate for the per person respect. That means sensible heat by per person 75 sensible heat is given. So the sensible heat per person is 75 into 80. Latent heat per person is 45 into 80. There is infiltration also takes place from point number 1. Outside air is directly entered into the room. The outside air is directly entered into the room, due to which the latent heat is entered directly into the room and the sensible heat due to infiltration is entering into the room. We have to find out the enthalpy at point number 1. We have to find the enthalpy at point number A. We have to find out the enthalpy at point number 2. That means enthalpy at point number 1 is 90. At A 61.3. At 2 it is about 45. So due to infiltration, this much amount of latent heat, H1 minus, this is H1 minus HA, this is HA, H1 minus HA into mass of air flow rate. That's mean H1 minus HA, this is latent heat, and this portion, the straight line in which the humidity is constant, specific humidity is constant, but there is increase in temperature. That's mean this is sensible heat parameter. So we will calculate the sensible heat. We have to calculate the mass due to infiltration. This is the mass, volume is given 18, and the specific volume we have to calculate. This is the specific volume line. These are the specific volume line. This is 0.90, this is 0.95. These two lines. That's mean this point is 0.91, 0.92, 0.93, 0.94, 0.9. This is 0.91. It is just lower than this point. This point is just lower than this one. That's why this is 0.9095. So through this we calculate the mass of infiltrated air 19.79. Sensible heat due to infiltration is M1 into latent heat. This is portion of latent heat into latent heat due to infiltration M1 into this is the portion of latent heat. This is the portion of sensible heat. Through this we calculate the sensible heat due to infiltration. This is latent heat due to infiltration. After this, the light load is given sensible heat. The glass load is given in form of sensible heat. After this, we have to add all the room sensible heat factor, room latent heat factor. We got the room latent heat and room sensible heat. We put the value of latent heat and sensible heat in room sensible heat factor. This is room sensible heat upon total heat. We got 0.732. This is the point. This is room sensible heat factor line. We have to find out the 0.732. Room sensible heat factor 0.732. We mark the 0.732 over here. We also draw a point, that alignment circle, which is at 26 degrees Celsius dry bulb temperature and 50% RH. This is the point of alignment circle AC. We directly join the line of the alignment, we join the point alignment circle and the room sensible heat factor point. That means this is the blue line, shows the line of room sensible heat factor. This is, after this, there is a parallel line, that green line shows, which is parallel passing to the point number 2, the inside condition. That means this is the condition over which the room, the air entering to the room exists. That means draw a parallel line with the blue line. This is a green line. This green line shows what is the condition of air entering to the room. जो भी पॉइंट आएगा वो इसी लाइन पे ही एग्जिस्ट करेगा, इसी लाइन पे. दैट्स इज रूम सेंसिबल हीट फैक्टर लाइन. जो भी पॉइंट आएगा, दिस इज 4 पॉइंट कंडीशन एग्जिस्ट ऑन the point number 4 condition exists on same line, this line. So after this, we have to calculate that 6 and 4 value. I also explain the bypass factor for heating coil, bypass factor for cooling coil. Through this, I will explain the bypass factor for cooling coil. TDB4, TDB6, we have to calculate, find out by hit and trial method, trial and error method. The point 1 is given. 27 we have calculated at point number 3. 27 is calculated at point number 3. We have calculated 4 and 6. We got TDB4, dry bulb temperature at point 4, dry bulb temperature at point 6, 9.6 and point 7.6. We mark 9.6 over here. This is 9.6. 9.6. This is 9.6. 9.6 and 7.6. We got this point. We have to mark this one. We join 3 and 6. 3 passes over the 6, we got the 4 point. 3 passes over the 6, we got the point number 4. 3 passes over the 6, we get the point number 4. That means this is the condition which enters to the room. Air condition which is enter into the auditorium or a conference room. We got this point. This is a room sensible heat factor line, green line. And if we join point number 2 with the 6, it is effective room sensible heat factor. It is effective room sensible heat factor. We move this backward. We go, this is 0.69. This is effective room sensible heat factor, which is by the joining of point number 2, room condition is directly connected with the ADP, Apparatus Dew Point Temperature. This is TDB6. After this, one point is more missing, that grand total heat load. That grand total heat load is outside air total heat. This is a formula is given 0.02. VF is volume of fresh air is given H1 minus H2. H1 minus H2, this is H1, this is H2. Enthalpy at 1 and 2. We go 72 kilowatt. GTH, grand total heat, which is room sensible heat. We have calculated room sensible heat, room latent heat, outside air. This is 35.38. We go room total heat, room sensible heat, room latent heat. And after this, we go grand total heat, which is room sensible heat, room latent heat, outside air total heat. This is 120.34 kilowatt. So thank you guys. If you like this video, please comment on this, press the like button, subscribe the video. I will add more lectures on load calculation, because load calculation is most important in case of air conditioning. So thank you very much.
है वतन वतन मेरे आबाद रहे तू, है वतन वतन मेरे आबाद रहे तू, मैं जहाँ रहूँ जहाँ मैं याद रहे तू, मैं जहाँ रहूँ जहाँ मैं याद रहे तू, है वतन मेरे वतन.
Subscribe to our